before we look at confidence intervals using very small samples, I'm going to start rather with this idea of comparing two sample means. We'll then apply it in the case of a small sample and how you would create a confidence interval. So comparing two sample means, we've got, say, two groups, Group A and Group B, and we're going to compare them for some kind of measurement of some sort. Imagine a sample mean. So two groups, maybe some kind of medical test, and we're going to give them some kind of drug or medication, and then compare, for example, blood pressure, average blood pressure, or say red blood cell count or something of the sort. So we'll have a sample mean from Group A and a sample mean from Group B, and we'd like to compare them to see if there's a distinction or difference between the two. Some terminology, first of all. The term placebo, or sometimes what I call nocebo, means, in effect, you give to Group A, or sometimes referred to as a control group, basically a saline solution, nothing. So one group receives the new medication, the other group receives nothing, and then we'll compare them to see whether or not this new medication has any difference. Often this is done with what's called a double-blind test, meaning to say that the individuals themselves do not know which group they're in. There's sometimes something called a placebo effect. Simply getting treated means that people feel better, or they change somehow their behavior. In addition, the double blind, because the people providing the medication don't know whether the person is in Group A or Group B. That means to say the placebo effect even goes to a second level, where the person administering can have some effect on the health or well-being of an individual. So this is called a double-blind test. Some other points of terminology, something called a matched pair. You sort of imagine we've got the two groups, and classic examples, identical twins. So now we can match up the person in Group A with an identical person in Group B. This is sometimes called matched pairs. In fact, the matched pairs goes well beyond identical twins. You can think of it as a case where in some way there's some method in which we can match a person in Group A to a person in Match B. It's the simplest way to compare two sample means. That's what we're going to be doing in the lesson today. Another example of terminology is pooled data. This means that I'll take some kind of information from Group A and combine it with Group B to have some kind of collective group in order to be able to make some kind of analysis. Which leads to the next point. Often the two groups are not even the same size. They're completely different people. One may have one set of people, another group different set. Sometimes the assumption is made, referred to homoscedastic, is that the standard deviation or the variance of Group A and B are the same. Sometimes heteroscedastic, that means that the variance of the two groups are different. So a whole series of assumptions or terms that are used when making these comparisons. I'm going to keep it to the most simple one, which is called matched pairs, and it won't even be identical twins. Instead, what we'll be doing is looking at an individual before and after a particular change or test of some sort. Another point of terminology is sometimes this is referred to as a one-tailed test or a two-tailed test. We've sort of seen this indirectly. A one-tailed test is the case when we had the chi-squared test, if you remember. There was only one gray area. It was on the right-hand side. Two-tailed test, we've kind of seen it indirectly when we had the normal curve, because it appeared the area was on both sides. In this case, I'm going to keep with the two-tailed test. It's just easier to work with for what we'll be doing today. Finally, there's something called the t-statistic, which we'll talk about later in the course. T-statistic is a bit like the chi-squared. We'll have a specific number, amounts to being a normalized statistic, and then we can compare it against a table, rather a graph, to see whether we'll accept or reject some kind of a hypothesis. Bear in mind what we're doing. We've got two groups. We're going to be comparing the sample mean of one group with the sample mean of another group, so we'd like to know whether there's any difference in the sample means. Now, it's unlikely they're going to be the same number, but how close is close? So the term that's used here is statistically significant. That is to say, can we really determine or distinguish a difference between the two, or is the difference simply a question of chance? So here's the simple example I'll be using, is to wonder whether or not students learn anything. So imagine I give a small group of students a test before taking this Quantitative Methods course, and then at the end of the course I give them also a simple test to the same students to see whether or not the results of the first test are in any way different than the second test. So in this case, what would the null hypothesis be? Well, the null hypothesis in a criminal trial is that the person's innocent, they should never have been arrested, and in this case it would be like saying, well, the students didn't learn anything during the course. There's no difference between the results of the first test and the second test. So here I present the results for 5 students, and you can see that the first test, and I've got the same students. So these are matched pairs now, because we can match up the individuals between the two groups. first test is group A, second test is group B, and I can calculate the mean. I've done it with the results here. We've got the average for A and the average for B. There's a slight difference. The question is this difference significant in the sense that we can say that this is not due to chance, or maybe it's just chance? It seems rather small, the difference. Now, to go about this test, rather than compare the two means directly, I'm going to do something different. I'm going to create a whole new variable, let's call it D, in which case is the difference between the two tests. So you can see that it could be plus or minus. First person, the difference, their test mark improved by 6. The second person, Boris, it decreased by 2, and so on. Now, if we were put this into a null hypothesis, we would expect D, the difference, on average to be 0. So that's a mathematical definition of the null hypothesis. We could use the Greek letter delta because this is D is a Latin letter, meaning the sample. Delta would be the population. We'd expect it to be 0. That'd be the null hypothesis. Individuals, of course, it's just chance. The number is going to vary between around 0. One expect it to be close to 0. So, first step is to calculate the moments, first, second moments of this new variable D. I've done that here. Add them together, divide by sample size is 5. We've got the sample mean D bar is equal to 3. Next step is to determine the variance or the spread of these numbers. So we do the deviation from the mean. 6 minus 3 gives us 3 for Albert, and so on and so forth. We added these numbers together, by the way. The sum of the deviations would give us 0. So we're going to square these deviations, which is the next step, and sum them. We've got the sum of the squared deviations is 70. This is a sample. We're going to use this as an estimator of the population standard deviation, so I divide by n minus 1. This 17.5 is the sample variance. Take the square root. We've got the sample standard deviation. So the next step now is to create a confidence interval, and we'll do this around the known sample mean. I'm going to change a little bit here the notation, because rather than x, I'm going to be using d. So here I've got the confidence intervals d bar plus or minus the z, which we can look up in the table, and the estimated standard error. Except there's a key problem we've got. We've got a very small sample, 5. And in this case, we can't use z because it's too small. In effect, what we've got to estimate two parameters here, the mean and the sample standard deviation. Well, we're using the sample standard deviation and estimator for the population standard deviation. It was a statistician, a brewmaster at Guinness. You can check this on Google, student Guinness, who noticed this problem, and so he then calculated something called the T table, and it's known as the T of student. And so that's what we're going to be looking at. It replaces Z for small samples below about 30 or 40 or so. One of the points of the T table is that T is larger than Z, so it means that the margin of error is going to be a bit wider, and so that we'll have a better idea of the accuracy of this confidence interval we're creating. It has to be wider because we're not so precise, because we have to estimate both the mean and the standard deviation. So this new T of student requires both the confidence level and also the degrees of freedom. We'll do that next. So here I've repeated the confidence interval with the T of student. We've got the average D standard, the sample standard deviation, and the estimated standard error. The estimated standard is 1.503. We can see it put in here. Now, in this case, for the T of student, degrees of freedom are defined as being n minus 1. So the degrees of freedom for this case are 4. And now we're going to look at the table. The statistical table requires us degrees of freedom. Here it is here. And I've got 4, and then we need a level of confidence of 90%. That means alpha is equal to 10%, and we're going to have 10% divided by 2, so it'll be alpha over 2 is 5, in which case we can see that the critical T value is 2.132. Degrees of freedom are 4. 0.05 is alpha over 2, so we've got 2.132. And that's what we put in here. There it is, the critical T value. That replaces our Z, so now we can say the mean is 3 plus or minus the margin of error, which is T times the estimated standard error. Rounding, we get 3 plus or minus 3.2. Means the upper bound is equal to 6.2, the lower bound is minus 0.2, and we can say now that we'd have to, at a 90% level, accept the null hypothesis because 0, in effect, could be inside our estimate. So it's possible, since the confidence interval goes from minus 0.2 to plus 6.2, 0 is inside, we'd say that at the 90% level, the hypothesis level is accepted, or the null hypothesis is accepted. We can do this by a slightly different route by taking what's called the t-statistic, and to do that, we assume the null hypothesis is true. That means delta is equal to 0, so we can rewrite the confidence interval this way. Rearranging things, we now have t, and instead of looking up t in the table, I'm actually going to calculate it as we do here. So the t-statistic is defined as being simply d bar divided by the standard error. Very simple to do. These are the numbers. Rounding, we get 3 as the numbers before, and now the t-statistic is equal to 1.6. This is quite handy because this is normalized, in effect, because we're dividing by the standard error. A nice rule of thumb to use on this is that if d bar is close to 0, that means the t-statistic is close to 0, in which case we would accept the null hypothesis. On the other hand, if d is far from 0, then we'd say, well, it's unlikely that the null hypothesis is true. Since this is normalized, we can say that if the absolute value of t is greater than 2, then we can reject the null hypothesis. So this t-statistic is very commonly used as a t-test. Another way we can look at this is go back to the statistical table. We know the t-statistic is equal to 1.6. So if I go back to it again, you'll see that t must be somewhere between 1.533 and 2.132. So we've got these two numbers here. You can sort of estimate what the prob value would be because it must be between 0.1 and 0.05, closer to 0.09 or so. If you use Excel, it will t.test, the function, it will tell you it exactly. I did that here, in which case it comes out to be 0.092, 9.2%. Bear in mind what the prob value, the p-value is that it's the probability that the null hypothesis is true. So at 9.2, it's fairly high. I'd be inclined to accept the null hypothesis.